Hello, welcome back to the Valve Studio. This is Craig, and I got a viewer question today. The viewer writes in, I often wondered about but never found a reasonable explanation for in tube data the plate-to-plate resistance and thus the primary impedance of the output transformer varies dependent on plate voltage, and the impedance seems to decrease as the plate voltage increases. I assume this has to do with Ohm's law and the relationship between R, V, and I, but the relationship seems to be contrary to simple calculations and altogether vague. Can you clarify this topic for me? Well, that's what we're going to cover today. I can say that it is Ohm's law, but it's a little more complicated than just a yes or no answer. So we're going to go ahead and dig into this specifically. I wrote him back and I said, what are you specifically looking at? And he says, push-pull circuits with 6L6s. So now we're going to look at an example for that today, and we're going to look at about all the variables that are involved in designing a push-pull circuit with pentodes, and the relationship between the speaker, the turns ratio, impedances, power supply voltage, plate voltage, screen voltage, bias point, and all those things combined together, and what kind of flexibility you have when you're designing with pentodes in an output stage. So we're first going to switch over to this screen here. About 4 years ago, I looked at a rule that seems to be apparent in a lot of these videos on YouTube about biasing push-pull amplifiers. I have a JCM 800, and I wanted specifically to know why is the bias point set at 70%? Why is that current set at 70% of the maximum? And it turns out that I spent a fair amount of time researching that, and I determined that 70% is actually a really good value for EL34s. We'll look at a little bit more of that today and why. We're not going to look at the 70%, but we're going to explore a little bit more about the selection of the different variables that you get to choose when you're an amplifier designer. So the first page we want to go to before we start here, back when I did that video, I created a Jupyter notebook. We're going to be running it today. I copied that, and we have a specific example for today's video using the 6L6. And we will talk about that in just a minute. So we're going to switch over here. The first thing you want to look for, or actually go and read, is this push-pull output stage from the Valve Wizard. This is the text description of everything I'm going to cover today. If you want to go look at that, you probably should pause this video, and this is down in the show notes, and go read that, and then we're going to explore some topics in here in a lot more detail, and we're going to actually show you some graphs that he shows you, but we have a lot more flexibility in the way that we can change the graphs and do a lot of different selections. All right, so it's a very interesting read, and it does tell you exactly how this ends up working and how that reflected impedance actually is when you look at the plate to plate. When you're doing Class A and Class AB operation, the actual impedance seen by the individual tubes varies over the swing of the output voltage, which is, we're going to talk a little bit more about that today, actually probably a lot more, and we're going to go into that with our example for 6L6s. He uses the EL84s, but it's the same idea. All right, so we also talks about the selection of why you want the grid voltage 0 graph and your load line to intersect below the knee. That has to deal with designing what kind of performance you want to get out. If you want a clean performance for hi-fi amplifiers, you want that to be above the knee. If you want to be maximum power output, you want it to be right at the crest of the knee. And then if you want a little bit of distortion characteristics to occur, at high volume levels, you want to pick it below the knee. We'll talk a little bit more about that as well. And then eventually comes down. He talks a little bit about biasing and the choice of biasing. He shows you this particular graph right here, which is it's called a composite graph. And oops. And the composite graph shows you both sides of the plate characteristic for both sides of the tube overlapped on top of each other to kind of show you what the overall load line is going to be. We'll show you that. And finally down here he calculates the output power. So just go start out by looking at the valve wizard and what he has to say about that, and we'll get into more detail about that. So the data sheet I'm going to use is from Frank's data sheets. We're going to look for 6L6, so I come to 6, and we come over here, and then we're going to go down to 6L6. 6L6 starts here, and it goes down to all the way to here. So typically when I pick out a data sheet, I look for a General Electric data sheet, because if particularly it's newer General Electric, they seem to be a more complete graph set for designers if you use the General Electric one. So we're going to pick the 6L6GC, which is this one right here. We're going to pick this one right here. So if we open this up, go ahead and widen this up a little bit. Things we're going to look at right now are these are the design maximum values. We can go up to a bias point of 500 volts on the plate. Screen voltage can go up to 450. The plate voltage, plate dissipation is 30 watts, and the screen dissipation is 5 watts. All right, so those are the maximum values that the engineers at General Electric advise you to use. If you exceed these, you're liable to potentially degrade the life of the tube. And then down here you have another, on page 2 you have different amplifier characteristics or suggested values. And the reason why, let's go back in time and look at the mindset of the engineers back when they were actually designing tube amplifiers. And the reason why General Electric gives these tables out is to give engineers a starting point for their designs. And if you use these values, in our case we're going to use this push-pull class AB1 amplifier for values for 2 tubes. If you use these values, then you're going to get the best performance. Now back then the best performance was lowest distortion, or lowest distortion versus power output. And if you just choose these, you're gonna make a fairly a good amplifier that has low distortion. But in our case, for guitar amplifiers, we actually want to detune the optimal performance so that we generate distortion. So these are a starting point, and they're valid. But let's look at the viewer's question. The viewer's question says, why does the output impedance of the transformer decrease as the plate voltage increases? All right, so let's look at these. Let's look at this first column and the second column. First column, we're at plate voltage of 360, and the primary impedance, the plate-to-plate load resistance, 6,600 ohms. 450 volts, which is an increase in plate voltage, it goes down to 5,600. His question is, why is that? We'll get into that. But here's the real question. This column here, this is going to lead us to an example. 3,800. If you look at these values, the first two columns are almost identical in all their values, except for this one right here, 66 and 38. There's one big other number. Power output of this is 26.5, and this one's 18. They give us these two columns because why would they give us those two columns? Those two columns are based on the fact that maybe you have two different output transformers with the same speaker. And so two different output transformers, the turns ratio are going to be a little bit different, so the reflected impedance is going to be different. And what should you expect if you have a turns ratio of, I think the first one is 29, maybe it's 27, the other one is something else. This is what you should expect from a distortion characteristic and power output if you choose an impedance level of that. But that's just everything being equal. You get to choose. You can estimate your power output. But the viewer's question is, why are columns 1 and column 3 different? That's what we're going to talk about. All right, let's continue on and look at some of these graphs. And this is the reason why I chose General Electric, because there are lots and lots of graphs in here. So what we are going to look at is, here's where you're using a triode connection. This one here is average plate characteristics when EC2 is 250. The EC2 is the screen voltage at 250. And this one, the top line is EC1 is 0 volts. So you use this graph here, this data here for when you do not want grid current. So that is for class A and A1 and class AB1 designs. You don't want screen current. This next graph down here, EC1 goes up to 20 volts. A lot of these power tubes you can drive positive grid. You can drive positive grid voltage, which means that current flows into the grid, but you have to take care of the output impedance of your driving circuit and be able to handle that. So if you're going to design A2 or AB2, you can look at this particular curve, but most guitar amplifiers, just to keep it simple, they don't have grid current, so we're not going to look at any of these characteristics where EC1 is more than 0. There's a transfer characteristic there. This graph here is the average plate characteristic. If you hold EC0, which is the grid voltage at 0, but you vary the screen voltage, what is the highest line you get out? So at 400 volts, you have 400 down to 50. So if you don't know, we're gonna show you this today as well. This 250 line right here, this line right here is the same as this line right here. Okay, because we're at 250, EC1 is 0. So this line is the same as this line. The point of this is that I'm bringing this up, if you don't know, the screen voltage gives you a plate characteristic that looks like this. So you got a graph of lines like this with different grid voltages as they decrease. And if you change the screen voltage, keeping everything else the same, if you increase the screen voltage, these go up like this. If you decrease it, they go back down. So if we're only looking at this top line, this one goes up and down based on the screen voltage, which is what this plot down here is actually showing you, this one right here. And that's an important thing for us to cover in just a minute. All right, here's the plate characteristics when EC2 is 400 volts, but this one goes up to 20, so we don't want that one. This is for A2 or AB2 operation. Here's our data right here. We're going to look at this column right here where EC2 is 400. The screen voltage is 400. AB1 operation, no grid conduction. All right, so that graph that I just showed you is effectively this column right here. This is where we are. We're going to be at our screen voltage of 450 volts. And that's important to know. And we don't look at any of those other. So what I did was I took this data here and I put it into my tool that is this one here, and I use this thing called the Engauge Digitizer. Let's open this guy up. So this allows you to import a JPEG or a PNG and actually put dots on the graph, and it will basically output a CSV file. So I have a lot of videos on the process that I did for that, but I get basically a CSV file out of this, and I'm not going to show you any of the code. I'm going to go full screen. I'm going to run all these cells. This is like I said, it was a Jupyter notebook, and we are going to run all the cells, and we're going to come down to this last cell, which is where we are going to do all of our analysis for what we're going to cover today. So again, like I said before, I am looking specifically at this column of if I design an amplifier to these values, what should I get out? And what is the load line? What would the load line look like if I'm running an AB operation? So that's what we're seeing down here. I took that 400 volt screen voltage, I put that in, and I put in that we have a screen voltage of 400, a plate voltage of 450. The plate current right here says 116, but that's for two tubes now. So one tube is about 55 milliamps. So I set the plate voltage at 55. And my speaker impedance, I just came up with these. I'm just using an 8 ohm speaker. And the turns ratio of 27 gives me a plate-to-plate impedance of 5832. They suggest you have something at 5600. So we're close. We're close enough. And this is what the load line looks like. But there's two load lines actually here. This load line, this purple one down here, is when we're running both tubes at the same time. So in push-pull output stages, they can be class A only, or they can be class AB, or they can be class B. And if you've taken any electrical engineering classes and you know about push-pull circuits, those amplifiers have distinct characteristics. But when we're picking the bias point, we get to choose where we are. Do we want it to be a Class A amplifier for push-pull, Class AB, or Class B? And we'll show you that in a minute. But this load line here is the slope when it is running in Class A, which means that both tubes are conducting at the same time. Both output tubes are conducting. And they're both contributing to the current going through the output transformer. And when that's the case, both tubes, let me do it this way. When both tubes are this way, they share the reflected impedance. So the impedance that the individual tube sees is half of the reflected impedance. So that's a particular slope of the load line. When you go into Class B, one tube is off, but the other tube is all the way on. And when it goes into that mode, when the one tube is on, now that particular part of the tube is going to draw more current, which works out that the impedance is down by it's a fourth of the reflected impedance. So in this case, down in Class AB, which is down here, each individual tube now is 5800 divided by 2, which is, I don't know, what is that? I can't even do simple math anymore. 58. That's 2900 ohms. And when it gets down, when it goes and it switches over to only being class B, which means that one tube's on, the other tube's off, that's half of that. So that's what, 1450? It draws more current when it's doing that. And so that load line's different. So that's why there's these two different slopes. And this transition right here occurs when we switch from AB to class B. It's shown as an abrupt change on my tool here, but it's not actually abrupt. It actually is very gradual, and you don't even detect this with your hearing. The reason why you don't see this in your performance is because there's actually two tubes looking and working at the same time. So I'm going to pull up the composite drawing. Remember, the composite drawing is where there's two plate characteristics put on top of each other, so you can look at both of them in a combined mode. So I'm going to turn this composite on, and we'll see the two composite graphs on at the same time. And so up here, the upper tube is actually contributing to all the current only. And then down here, when the voltage is really negative, the bottom tube is carrying all the current. But in the middle, both tubes are carrying the current. And so what effectively, the load line is a straight line, even though there's this discontinuity that occurs on both the individual tubes. All right, I hope that makes sense. And this is what makes it so that these two tubes combined could generate more power, because you're swinging over a wider voltage. All right, let's with this tool we have the flexibility of changing everything having to deal with our output tube design, or push-pull design. We can vary the plate current, we can vary the screen voltage, we can vary the plate voltage, we can vary the speaker impedance and the turns ratio. So the first thing I want to talk about is varying. What do we want to change? Oh, let's. Okay, a lot of people don't like to work in this composite mode, only because they're just a reflection of the other. So if you can think only in terms of one half, you'll get and just multiply times 2, or know that there's another tube doing the exact opposite on the other side. So I'm going to turn the composite mode off. That makes our graph a little bit bigger. And remember, I talked about this particular feature of a vacuum tube is, where's that graph? This one here. This is showing you when you change the screen voltage, those curves move down and become closer together, or if you increase it, they move up. So we can see that in the tool. If we change the screen voltage, what you're going to see, if it's at 400 now, if we change it, I'm going to move it down. So these are actually going to become closer together and actually move down. And you'll see that they're moving down. Now the load line hasn't changed at all. These characteristics are changing as a function of the screen voltage, but the load line is still the same, because the load line is set by the impedance level of the speaker and the turns ratio. All right. So back up at 400. Now what happens if we change the plate voltage? Plate voltage is somewhat fixed, because you are dependent on your power supply voltage, and you're also dependent on a little bit of the output transformer resistance. So you're going to get a little voltage drop in the output transformer, but it's not much. So your plate voltage is basically sitting really close to the power supply voltage, that you get out after all the filtering. And what happens if you change that? So if you change that, what that effectively does on your load line is it moves this point down here, the blue dot, is it moves it back and forth on the x-axis where the current is 0. So if we go down, it's going to move it down that way. But the load line itself is just moving linearly in the x direction. It's not changing its slope at all. It's just moving in that direction. So you can move it forward and you can move it back. If we put it back up, let's say we put it at the maximum level, which was 500, we move way back over there. However, when you move over this far, what you've done is you've now crossed over the dashed red line, which is the power dissipation of the plate itself, and you're going to risk premature aging of the tube, or you'll burn it out. That's what, if you get above this, if when you're in class A and this tube is on, you're running the risk of exceeding the power dissipation of the plate. Okay. So 500 volts is not good for that. Now, if we vary this plate current, what we're doing is we're moving the curve, our transfer curve up and down in Y. So we'll show you that. So we're set at 55 now, and we're going to move it down. So we're now effectively moving only the class A portion of the transfer plot, the load line. We're only moving it down. We're not changing B at all. We're only changing A, because B is set by the plate voltage. I mean the basically the plate voltage and the screen. No, what's the plate voltage set on? Oh, what is it set on? Oh, the line. Duh. The line, the brown line is set on the actual impedance of the output transformer. Brain fart. So that doesn't change. So we can now move it in X by changing the plate voltage. We can move it in Y by changing the plate current, and we can also change its slope by changing either the speaker impedance, or we can change the turns ratio of the transformer. So we'll show you that next. So let's go back up to 55 where we are. Let's go back to our resetted values, which is 55 and 450. This is where we started. So if we change the speaker impedance, we're going to change the slope of this line. So let's go, say we put a 16 ohm speaker in the amplifier, and we drive it that way. So we've changed the slope of the brown line effectively. And if we go back over to 4 ohms, we've made it steeper as well. So between all those things, those three things, we can move that load line kind of wherever we want on the characteristic, the plate characteristic, and we can also change where those positions are. So we have a lot of flexibility there. And if we had the infinite amount of flexibility in which we could change the power supply, we could change the screen voltage, we could change if you change the power supply, we effectively change the plate voltage. We can change the screen voltage through biasing. We can change the speaker impedance by choosing a different speaker. We can also change the turns ratio by choosing a different output transformer, or winding your own for custom turns ratios. So with all that flexibility, that lets us decide what kind of performance we're going to get. Now let's talk about performance. If you are operating in Class A mode over the entire amplifier, you're going to lose out on power output, because in Class A mode you need to be below the 30 watt range. So let's see what if we operated only in Class A, which means that both tubes are on all the time. Let's go see how much power we could get out. So we need to, looks like we need to reduce the slope of this line down. So let's go back up to 8 ohms here. And let's move the line down. So let's change the plate current down a little bit. So we're working below our power dissipation. And so right there, if we were only in class A, we would result. Well, actually, we would result in this operation here. This is not only class A. Well, this is class A and class B because over the full swing, we're going to switch in zones. So we need that intersection point, that purple point, to be way up, way up, way up here, near the 0 point line. So if we needed to have a larger turns ratio on our output transformer. So I can only go up to 40 on this, but you'll see that our power output goes down significantly. We're down to 27 watts. Okay, so but if you notice, we're way down below the line here. We're way down behind the power dissipation, so we can increase the plate current and move that line up a little bit. All right, so that's all class A. Both tubes are fully driven the entire time, and we're still at 27.4 watts. The advantage of using pentodes in push-pull is that you can go to class B. Now, class B has a unique feature about it that class A doesn't. Class A, you want to be underneath power dissipation at all times. And this green dot right here is the one you want to have 70% lower. That's the recommended kind of bias point in the ballpark to have that. So we don't want to run it that high. Now in class B, let's go back. Let's reset everything back to where we were. So we're at 55 and what was that, 27? So this is our amplifier here that we are designing out of data sheet, which is this last column on the data sheet. This column here. Now when you're in class B is one tube is all the way on, the other tube is all the way off. So no current's flowing in the tube that's off. So when you're in class B, if you're doing push-pull, you can exceed the power dissipation curve because you're only exceeding the power dissipation on half of the waveform. The other half of the waveform, the tube is off. So you're effectively having the amount of power that goes to the plate, which is going to lower how much heat it actually generates. So in class B, you can clearly exceed the power dissipation and not be concerned about blowing out your tube. Now there is a thermal response to the tube, but most class AB amplifiers are designed in this fashion where the B operation exceeds the power dissipation. And depending on how much power you want to get out, you can exceed it by a lot, and your tube will still not. You won't be in excess of the power limit itself of the anode. All right, so let's talk about the knee. All right, Valve Wizard talks about the knee. I don't think I have the Valve Wizard page still open. Yeah, I do. Let's look for the word knee. The line may pass above the knee for the triode-like operation, which is good for hi-fi. It's good for hi-fi because, where'd my graph go? See how much space is between these lines? Right here. If we were above the knee, this is actually fairly linear up in here, which means that the space between the lines is about the same. So that means that we're kind of linear. If we're below the knee, what happens is over here, as the voltage swing gets near this point, you get, because the lines are smashed closer and closer together, you don't get out as much current. So the resulting waveform is somewhat rounded off on the peaks. It's not squared off. It's rounded off, and this is a desirable distortion characteristic that you get out of tubes. So below the knee is good for guitar amplifiers. Above the knee is good for hi-fi. Now, in our situation, if we want to get above the knee, if we want to make a hi-fi amplifier, we're going to exceed the power dissipation on the class B portion of it. We're going to be up in here, okay? And that, you have to decide if that's going to be good or bad. However, you can move this whole set of curves down based on the screen voltage. So you can move that knee back and forth a lot. Like here, we're above the knee right here. If we set the screen voltage down to 250 volts, we get a little bit of decrease in the power output, but we're now more in a hi-fi type operation, and we're only exceeding the power dissipation by a little bit right in here. And we can change that by moving the current, by changing the plate current and moving that down. So if you went right here and you designed this 6L6 with this particular screen voltage and setup, you'd be running more on the hi-fi side, and you'd have better linearity itself at a with a loss of what 12 watts. So we're down to 38 watts instead of 55 or whatever it was. All right, so that's good. So let's talk about designing amplifiers. What do you have flexibility of? So typically you have a power supply. You have a power transformer, and you're going to decide between tube rectification or diode rectification, and then the applied voltage drop there. So that and the filtering, if you have a resistor in there or capacitors or whatever, the power supply is going to put out a voltage, and that is going to set the plate voltage for your design. On the output side, you're going to design for a particular kind of speaker and a particular impedance of a speaker, and then you have a choice of what kind of output power transformer you're going to use. And the output power transformer basically sets the turns ratio, which gives you the reflective impedance. So that's relatively fixed, as well as the power supply. So you can't change really the plate voltage. You can't change the reflected impedance. What you can change, you have two things you can change. You can change the plate current, which moves your curve up and down, or you can change the screen voltage, which moves the characteristic lines up and down. And between those two things, you can manipulate and live within the power limits, and you can also manipulate what type of performance you want to get out from a distortion characteristic. So to answer your question, I know it's been a long video. It's these values on the data sheets, wherever the data sheet went. These values on the data sheet are recommended by the engineers for engineers to design the most accurate amplifier possible. Not possible. If you pick these values, this is the anticipated power output you should get, and this is the anticipated harmonic distortion you should get. And all these data sheets are set up so that you basically optimize both of those at the same time. For guitar amplifiers, if you only want to do guitar amplifiers or hi-fi amplifiers, you can vary that plate-to-plate voltage wherever you want it. The plate-to-plate impedance wherever you want it by choosing a different speaker or a different output transformer, and it's got nothing to do with the voltage, the plate voltage itself. So I hope that answers your question. I know I went long on this thing, but if you want to play around with this, I encourage you to kind of get a feel for how this kind of functions and play with these sliders and see for yourself all the different things that change with these. There's 5 variables there, and how you can actually do output power stage in push-pull. So one last thing. When you're designing a hi-fi amplifier, you want matched output tubes. And you want matched output tubes because there's a lot of things you want when you're designing hi-fi amplifiers. On a hi-fi amplifier, you want to cross above the knee. All right, that's one thing. The other thing you want is the matching of the tubes themselves. Make it so this transition from here through this AB operation down to here, you want that to be as linear as possible. And so in order to get that to be linear, you got to have several things. You got to have matched power, you have matched tubes, you have to have matched biasing on those tubes, and you have to have a transformer wound such that the impedance or the resistance, the DC resistance of both of the legs of the output transformer are equal. And getting a transformer wound that way is more expensive than just winding it so that one leg is a little higher than the other. The reason is the way that they put the wire on the spool. They have to wind it simultaneously. I don't want to get into that, but on a guitar amplifier, you don't really care about any of that because that mismatch, all that's going to lead to is distortion, which you kind of want to introduce distortion on a guitar amplifier. So if you're reasonably in the ballpark of the currents, you're good. Or the tube matching, it's going to be okay. Or the output transformer, transformers wound for guitar amplifiers. They wind them so they're less expensive. And so what's going to happen is there's going to be a little bit of a this line is going to kind of do some kind of weird things as it works its way through, but ultimately having one tube work a little bit differently than the other is not a bad thing on guitar amplifiers. Okay, I hope that answers your question. That's what I got for today. Thanks for asking the question. It got me to be more familiar, and I updated my tool here so it's a little easier to use, and I added the composite feature, which is handy to see both curves at the same time. And I know that I helped myself being a better designer, knowing the flexibility of these 5 variables when I design push-pull output stages. All right, thanks for watching. This is the Valve Studio.